welcome to the Data Engineering Podcast, the show about modern data management. Have you ever woken up to a crisis because a number on a dashboard is broken and no one knows why, or sent out frustrating Slack messages trying to find the right dataset, or tried to understand what a column name means? Our friends at Atlan started out as a data team themselves and faced all this collaboration chaos. They started building Atlan as an internal tool for themselves. Atlan is a collaborative workspace for data-driven teams, like GitHub for engineering or Figma for design teams. By acting as a virtual hub for data assets ranging from tables and dashboards to SQL snippets and code, Atlan enables teams to create a single source of truth for all of their data assets, and collaborate across the modern data stack through deep integrations with tools like Snowflake, Slack, Looker, and more. Go to dataengineeringpodcast.com/Atlan today, that's ATLAN, and sign up for a free trial. If you're a Data Engineering Podcast listener, you get credits worth $3,000 on an annual subscription. When you're ready to build your next pipeline and want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With their managed Kubernetes platform, it's now even easier to deploy and scale your workflows, or try out the latest Helm charts from tools like Pulsar, Pachyderm, and Dagster. With simple pricing, fast networking, object storage, and worldwide data centers, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode today, that's LINODE, and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host is Tobias Macy, and today I'm interviewing Praneha Narang about her work at Aliro, building quantum networking technologies, and how it impacts the capabilities of data systems. So Praneha, can you start by introducing yourself?
Thank you so much for having me here, Tobias. My name is Praneha Narang. I'm on the faculty at Harvard. I also simultaneously wear a second hat as the CTO of Aliro Quantum, where we're building scalable quantum networks. And I'm really, really excited to tell you about what these are and how they might be able to make our lives better.
And do you remember how you first got involved in working with data management, or at least in areas that are adjacent to that space?
Absolutely. So I was a graduate student at Caltech and, just started thinking about how GPUs can have an impact in predicting various quantum phenomena. And, this is before everything was GPU enabled and well before people were talking about GPUs being a daily computational life. And that's where I really got excited about new computing architectures and have an impact on problems that are independently of interest. And that's been a theme throughout my career, throughout my time as a faculty member as well, where we've been thinking about, if you had the biggest, baddest computer, classical, quantum combination thereof, how would you use it to answer the most important problems facing us today?
That brings us now to the work that you're doing at Aliro. I'm wondering if you can share a bit about what it is that you're building there and some of the story behind how it came to be and why you decided to try and productize this and focus so much of your time and energy on it.
Yeah, absolutely. So, we started out, spun out my lab and a couple of students, me, and we started talking about what does it take to bring quantum technologies, quantum computing, and other aspects of quantum technologies. I'm going to dive into that in a few minutes to everyone. What does that mean, right? And this is now a few years back, before some of the big announcements in quantum computing that we've seen. And it became obvious that quantum devices in their current form, even if you take everyone's roadmap to be as canon, turns out that getting to scale will involve connecting these devices. And, that's just the reality of classical computing. We don't expect it to be any different for quantum computing for even more profound reasons than the reasons in classical computing. So we start thinking about, well, what does it mean to connect devices? And, should we think about it purely from a computing standpoint, or is it more general than that? And that's when my team got into, thinking about quantum networks, in particular, quantum networks that are scalable or universal. And the idea with these networks is that, it's not specific to connecting two endpoints or 3 points for secure communication. It's not specific just to connecting two superconducting quantum computing devices. It's more general than that. It's a network layer that can actually work with various different types of hardware, can work with different types of use cases. And that suddenly starts to sound like the early days of the internet, where we were starting to talk about connecting devices. Yeah, that's how we came to this field. It's a little bit different from where most people you meet in the field have come primarily from the cryptography or the secure communication side. We came at it from the standpoint of, what are general network pieces that will enable both computing and secure communication. As we were doing that, we also realized the third part of this triad is, of course, distributed quantum sensing, and the three go hand in hand.
And in terms of the initial use cases that you're targeting, I'm wondering how you went about that sort of discovery and selection process to understand what is the inroad to be able to say, I've got some functional capabilities. I want to start figuring out what is the product market fit. How do I determine who are the early design partners to be able to actually start putting this into production and stress testing the theoretical ideas in a real world environment?
The big hope here is a general quantum internet. This is, of course, going to transform our lives. You've probably heard this spiel from a couple of different people. And you start to look at, well, what is needed in order to actually make such quantum internet, quantum architecture at scale a reality? And it turns out we have some pieces of it today, right? So we have some devices that look like endpoints. We have some pieces of it that look like a network, but we don't have everything. And one of the biggest things we're missing, of course, is a quantum repeater. Now, before I dive into what's a quantum repeater, let me just take a step back and say that, when we think about networks, right, and when we think about quantum networks, we're really thinking about entanglement generating and using networks. And this is fundamentally different from some of the work you might have heard about from people in key distribution, for example, which, by the way, is a field that's been around for some time. So when you think about what it would take to get to larger distances beyond metropolitan distances, to actually have multiple points, a complex topology in this network, what it takes to include both terrestrial and satellite based pieces, suddenly you realize you need a lot of new quantum networking components. And some of these are commercially available now, and some are commercially available perhaps from just a single company. And these include things like quantum memories, quantum transducers, quantum frequency conversion, the list goes on. So our proposal, our idea was, let's start with a turnkey integrated prototype network. And in this prototype network, we take the best pieces you can get today, and we show you what this looks like as a functioning network, right? So you turn it on and something goes. Now, it's not going to be the speeds you want. It's not going to be all the use cases, functionality you want, but it will allow our customers to actually build the confidence they need in order to give us access to the fiber they have in the ground, or even to build a dedicated network for them. Because it's a big ask to tell people, we want to just rip out everything you're doing in networking today and replace it. Or, there are some ideas on how you could have both a quantum and a classical channel. There'd be some co-design. There are interesting design questions to be answered. So building these early networks, and it's, pick your favorite analogy, ARPANET, early days of Cisco. I mean, there's so many analogies here that whichever one resonates with you. But the important piece is that it's towards that connected quantum internet. And this is where you can imagine having not just secure communication, you also can imagine having your favorite compute devices on a cloud. This is perhaps the only way that you could get to blind quantum computing. This is where you want to make sure that people can't actually see what you're computing. It's something we take for granted in other contexts. And also distributed quantum sensing, right? So there's this idea, well, they're going to be quantum devices. They're going to provide us higher sensitivity, more information. That's great. It can all be connected in this quantum cloud. So we start to engage customers across that entire spectrum. I basically told you in tech terms all the people that we're working with. So we have folks who are interested in secure communications today, in various parts of the defense and intelligence communities, for example, various big corporations that have important data to protect. On the computing side, we have both classical and quantum computing folks who are interested. I, don't want to take this time to drop any names, but just to say that, there are various architectures that have been proposed, trapped ion, superconducting, they're purely photonic architectures. And then there are also ideas in how you could actually combine a couple of these into this best of both worlds type scenario. So use one as memory that goes with something that has faster gates being a concrete example. So one of the things that, when we start talking about this very, very complicated architecture, it has all this going on is, so are you going to go from concept to build on day zero? And the answer is no. In fact, like classical networks, we need to do a lot of simulation and direct emulation of various pieces before we get to the prototype. And within the Alero team, we've built up an in-house simulation platform. It's our in-house sandbox. We also have now an emulation platform, as you can imagine, with various quantum pieces. Each of these components, right, I mentioned a minute or so ago, has various parameters it needs to hit for this entire architecture to go. And so now it's a range of parameters. You can think of there being a minimum performance parameter. And then there's something that is perhaps more optimal that allows us to relax constraints in some other part of the system. And that kind of systems engineering is what we're doing within both the simulation and emulation piece while building these prototype networks.
A lot of different directions that I'm interested in digging into this. And one of the first things that I'm curious about is, given the fact that you are building this fully integrated system of various components, it's definitely very analogous to distributed systems problems that exist in terms of data management, data processing. And so that brings up the question of consistency and availability guarantees in the network layer and how you're able to model that, given the fact that you're dealing with probabilistic states and not concrete states of, on or off. You have to deal with what are the gradations of probability that any given piece of information has propagated to a certain point in the network.
Yeah. So actually, when you think about the underlying technology here, in part what makes the Alero network in a way universal is that it's an entanglement generating network. So it runs this nice link layer on a protocol that generates elementary point-to-point entanglements. And then it runs these network layer protocols that do the swapping, entanglement purification. Now, some of the things that we're talking about here with the layering, the layer structure, has direct analogies to classical networking, but some of the pieces are, different. And what we're trying to actually be cognizant of is that, the way you think about it in classical networking might not directly port over. There might be some differences. Of course, we don't want to reinvent things that people know, but we also don't want to force a mold onto quantum networking if there is a more natural way to do it. So, you can think of, I mentioned the word swapping and purification. So that's happening in the network layer. And the swapping here is going to pull together various different elementary entanglements together to get end-to-end entanglement that you're then delivering to the various quantum applications. So entanglement really is the resource that you're distributing across this network. Now, if you think of it as just the best entanglement I can generate, that is frequently insufficient. And this is, towards the probabilistic component that you pointed out. So you need to actually think about improving the fidelity of the entanglement. And that involves doing some form of purification or distillation. And there are various protocols that exist for this, some which I put out, some I've co-developed with Alero, and of course there are others in the community that exist. And you can think of these as trying to meet some quality of service requirements of the quantum application, right? So there's some amount of entanglement, and this is the worst way of thinking about entanglement because it's a very quantum resource, and I'm describing it as this very classical resource that some amount is going to get everywhere. But you need to hit certain thresholds for the application to actually go. And all of that is being handled, in our case, in the network layer. Now, this is in contrast with some of the work that's happening with, what people are doing in key distribution-based quantum networks. So I contrasted entanglement generating using networks, the fact that the universal networks with these, current QKD networks, because they're based on this prepare and measure quantum technology. And realistically, what that means is that those networks can only ever really be used for key distribution, because this idea of sharing end-to-end entanglement and using it as a resource for quantum applications isn't something that you could do with this network. And yeah, as you very correctly pointed out, this is all nicely happening in the network layer.
Another interesting element of this is the junction points between classical and quantum networks. And the obvious analogy is the junctions between fiber and copper networks that we have been going through the process of upgrading. And I'm wondering, what does that look like in terms of the actual handoff, and if there are any protocol translations that need to happen because maybe you're not using TCP over a quantum network, for instance, and what are the architectural locations where it makes sense to put in those junctions where you're going to say, this is the point where I'm bridging from my classical to my quantum network. So does it go into an ISP? Does it go into the data center? What do those design questions look like as you're starting to play with these network topologies?
It's very early days at the moment. So, what you can send over the quantum channel is very limited. And right now, you want to do as little as possible over the quantum channel and as much as you can over the classical channel. And that's just because, we don't have repeaters, or the repeaters that existed are embarrassingly slow. We're long ways from sharing, and people always ask me, well, will I be doing a Zoom call over a quantum network? And long ways from that. In fact, that itself might not be something that makes sense. So we're not replacing the classical network here per se, but actually combining pieces of it, doing things over the classical and the quantum channel somewhat simultaneously. Now, protocols need to be developed, and that's actually where a lot of ideas, including SDN, are crossing over from classical to quantum networks. I know classical networking, people are already writing SDN off, but quantum networking, we're still learning about SDN and thinking about what that means for quantum networks and how we can best use it. And this is where, there's the technology junction, but there's also the people junction that we're making, and slightly different from the point you perhaps asked about to us. But I just want to say, we have noticed that people who are coming from a classical networking background to quantum networking are really, really bringing something very valuable. It's preventing us from making some of the same mistakes, or perhaps going down the same rabbit holes that people would have in the early days of classical networks. And this is where, being Boston based has been great. We've been able to get top networking talent here, as well as quantum talent. Some other classical analogies that come to mind as we think about quantum network is, well, do we need something that looks like a quantum bus? Is there some fabric functionality? Is it all going to be, what's the Mellanox of quantum networking? How do I think about a bus? And I think all of those components are being developed, some by us at Aliro, and how they're going to be integrated into this, network that's going to be general purpose is still being figured out. So that's where we are with some of these technology choices right now relative to classical networking.
Another thing when you're talking about network technologies is, what are the ways that it's going to fail? So with classical networking, you can hit TCP congestion issues. You can have issues with BGP routes being wrong. You can have problems with, some undersea fiber cable gets cut, so you can't reach another continent for some reason. And all of the different failure mitigation systems that have been put in place as far as, traffic rerouting, TCP retries, all of these different things. And I'm wondering how that maps into quantum networks and some of the ways that you have been simulating those failure modes to be able to design for those eventualities.
Excellent question. Actually, some of the failure modes that you described are common to classical and quantum networking, right? So historically, if you think about classical networks, and not I say historically like they're gone, no, they still exist. You simulate and you model what that abstract behavior of this network looks like, and you emulate to see what the functional behavior looks like, and you see some complex system behaviors. Now we can simulate many, but not all pieces of a quantum network, and this is partly where things get tricky, because all of these quantum components that I pointed out, explicitly the repeater, is very, very hard for us to directly simulate, right? It's a quantum problem in itself. So that right there becomes a challenge. But I can better emulate it by, asking somebody for an actual repeater that I, together with the simulation, put into an emulation platform. And that's something we've been doing. This actually, allows us to think about simple problems like connectivity and queuing, complex problems like you pointed out, like congestion, thinking about new protocol design, fault management, and identifying network component failures is going to be very hard for, various quantum technology, just because so much of it is new, and there are, very few things that we know about how it operates in the field. So we're trying to de-risk all of that by figuring this out while we build these prototype networks.
As far as what it means for people who are working in the data space, what are some of the new capabilities that quantum networks can enable? What are some of the ways that quantum computing and AI running on those systems is going to change the way that we think about data distribution and data modeling? And what are some of the ways that it's going to stay the same regardless of which network technology you're relying on?
So this is a little bit of a convoluted answer, because how such networks will be useful to people working in various areas of data science in the near term goes through the route of quantum computing. So stay with me, right? And so it turns out that, existing quantum computers, they've been announced. People can do toy problems on these, but the valuable problems in convex optimization, the kinds of algorithms that have been proposed for quantum machine learning, for example, those are not accessible by current quantum computers in their present form. Things have not gotten to a stage where, you're seeing this practical quantum advantage in, say, logistics. People ask about that a lot because supply chain has been on everyone's mind, but there are other problems that roughly fall in that same category that you really can't access with quantum computers today. However, what you can do is go through a scale up approach, which goes through the route of connecting these quantum devices, right? So if you think of like a discrete GPU, now you can interconnect many of these using the kind of quantum networks that we're building. And this is why it's a universal quantum network, because the same thing we're building is relevant for scaling up quantum computers, and it's the same technology for actually doing secure communication. So if I use a classical analogy here, it's going to be necessary to build a multi-core, multi-processor quantum computer, right? And this is all so obvious when I say it, because people say, yeah, of course, Pri. But this is where, you have various quantum cores, processors, they're connected using a quantum bus. And, you have some multi-core QPUs then connected using a quantum fabric. Now, because we have a universal quantum network, our quantum network can provide the required quantum bus, this quantum fabric functionality, essentially generating these entangled qubit pairs between two QPUs in the cluster. You can basically integrate and you can think about implementing distributed quantum gate circuits and do the type of problems, right? This is ultimately getting to your question to us. How do I do one of these problems that are of interest to people, in AI today? And the path to that really goes through scaling up with these quantum algorithms, distributed quantum computers. So that's where I think there is a lot to be done in the near term, and where there's going to be a direct intersection between people in data science and people in areas of quantum networking and quantum technology.
Modern data teams are dealing with a lot of complexity in their data pipelines and analytical code. Monitoring data quality, tracing incidents, and testing changes can be daunting and often takes hours to days or even weeks. By the time errors have made their way into production, it's often too late and the damage is done. Datafold built automated regression testing to help data and analytics engineers deal with data quality in their pull requests. Datafold shows how a change in SQL code affects your data, both on a statistical level and down to individual rows and values before it gets merged to production. No more shipping and praying. You can now know exactly what will change in your database. Datafold integrates with all major data warehouses, as well as frameworks such as Airflow and dbt, and seamlessly plugs into CI workflows. Visit dataengineeringpodcast.com/Datafold today to book a demo with Datafold. As far as the actual sort of capabilities of quantum networking, does it break the faster than light problem that we have with classical networks because of the fact that you're dealing with entangled pairs? How do you manage that? What are the expectations that we want to set for people who are thinking about quantum networking and all of the magical, frolicking unicorns that it's going to bring to our data problems?
Okay, so we never go faster than speed of light. This paradox, thinking about entanglement and teleportation relative to speed of light, this has been resolved. Everything we're doing is well within the known laws of physics, and that's a good thing. In terms of where things are and when it's going to start to have an impact, right? Prediction is hard, especially about the future, and this is a moment where it becomes true. So what I can say is that connecting quantum computers, connecting quantum devices, these small networks, this is happening right now, okay? There are big networking companies, big telecom giants that are looking at quantum networking technology today. That's happening. Now, does that mean it gets to the end user in the next 6 months or a year? I don't know. I think it's going to take a little longer. Depends on who you define as an end user of a quantum network. Now, if they're thinking of, quantum computers, connecting quantum computers because they're trying to be the first to solve a very hard problem, yeah, you'll start to see that in the next 6 months, a year, because various quantum computing companies are talking about using such a fabric, distributed computing architecture using our kind of networks. So, but you're not going to be, asking for entanglement as a service to arrive at your home anytime in the next near future, at least. And that's because, we have various pieces of this technology that need to be figured out. especially as we get towards that quantum internet. And I think some of this has to really be in those network components that I pointed out. We have them in a functioning form today. They are far from optimal. So we need investment in this area.
Are there any sort of notable differences in terms of bandwidth capacity or overall end-to-end latencies that are available because we're using quantum networking? What do the limitations look like where people are used to looking at maybe 1 gig, 10 gig, 100 gig connections for, the different fiber interconnects?
Oh, I think at the moment we need a real throwback here. Think late 80s in terms of, speed, in terms of latency, in terms of, what you're expecting from the network. However, and this is the upside of doing it the second time, we're not going to go through the same slow technology progression that we did with the first wave of the internet.
For people who are now looking at using quantum networking to be able to bridge to their quantum processing units for doing quantum-enabled AI, how does that change the overall approach to thinking about the ways that they're structuring their delivery pipelines, their data modeling? Are they going to be locating storage directly adjacent to these QPUs, or are you going to be feeding reduced data sets into the QPU so that you're not trying to replicate your entire data store? Like, how does that shift the way that we think about our overall workflows?
Yeah, I think people are talking about, and not just talking about, but building quantum data centers already. And this is, towards, there's some proximity choices that people are making implicitly and explicitly, right? So I think that plays into the question you just asked. I think in terms of really modifying workflows and, making major changes to how people are doing things in AI right now, I'd say it's, not something that you should do on your next build cycle, but it's something that you should start looking at and thinking about. Is there going to be a quantum data center that is within X miles of where we're located? How would we integrate? Would we need to integrate? And I think those types of questions really should be asked. And in fact, they are being discussed, at various levels in the government. They're being discussed, of course, at various levels, big corporations. I hope that that information makes its way out to folks maybe who don't have an internal R&D arm that's looking at this area.
Other aspects of the networking layer of the data stack are things related to security, which you touched on a little bit, as far as because you're working with entangled pairs, you don't necessarily have to worry about the encryption protocol because it's entirely private due to the interconnect that you're building. But how do you think about sort of data privacy considerations in that layer? How do you map the handoff from the classical to the quantum network to manage some of those questions of data privacy at the different stages? And, maybe at the bridge, you say, I'm actually going to strip out the encryption because it is adding to the overhead of this transmission. So we can actually optimize the transmission from the quantum bridge into the quantum computing unit, and then being able to re-encrypt on the reverse journey.
There are various vulnerabilities of the network, some that are physical, some that are at the handoff, and some that, of course, are the network layer. So you get physics-based security in quantum networks. That's something that everyone hears about, everyone talks about. I think what's harder is when you're, using both the quantum and the classical channel to figure out all these other side channel attacks, to figure out all these other vulnerabilities. And we're working with, customers to identify problems that are specific to how they're going to deploy these networks and how we're going to, protect against attacks like that, especially of interest to our intelligence community customers.
And so this is definitely a very interesting and nascent field that has a lot of potential for future development. And a couple of questions related to that are, what are some of the timeframes that we're looking at for actual practical adoption of these capabilities? And for people who want to get involved with this space as either implementers or early testers of these capabilities, what are some of the useful on-ramps to that?
Excellent question. And, I want to point out that there are various companies that are hiring in this field already. And we've only seen that hiring ramp up over the past year. And based on where folks are headed in quantum computing, quantum networking, I think the demand is really growing. So for folks who are on the classical side, I encourage you to think about this as the moment to make the jump. Few reasons. One, of course, as I was pointing out, the background people have in classical networking is actually going to be important towards enabling these quantum networks. And towards that, various conferences in classical networking have started to do various small, your first day of quantum networking type sessions, organizing a couple of things with IEEE to actually get some nice pedagogical review articles out. There's been an explosion of people who've said, hey, is there a good textbook? I know there are efforts to get accessible quantum networking, digital textbooks out that people can actually start on and look at some of these interesting problems, see them framed in a way that is reminiscent of what they've seen in classical networking previously. This is not an area where we've started to have the kind of open source lectures that you see on the quantum computing side, but it's come. So the second thing I want to point out, especially to people who are graduating or, going back for their masters, think about taking, a class that roughly touches on quantum, because I think a lot of the time that people spend in making the jump is spent on, jargon, figuring out some of the notation. And that's all it is really. It's notation and jargon. It's conceptually not particularly challenging to follow for people who have a STEM background. It can really make you very valuable to companies looking for people in quantum networking and quantum computing, especially software developers, particularly, people who have a background in large infrastructure, thinking about distributed computing. There's a lot of demand for those folks on the quantum computing side, and it's not going to be satisfied by the number of people we train in, say, theoretical quantum information.
In terms of your work on building Aliro and experimenting with these early quantum networking technologies and interacting with design partners, what are some of the most interesting or innovative or unexpected ways that you have seen these quantum technologies used either for just networking in general or for data systems in particular?
I've been pretty surprised by how people who are doing quantum sensing, long baseline astronomy have started to actually connect these and use networks to connect various sensors and do experiments that you would not necessarily think of, without that quantum enabled system. So that was pretty exciting. I can't think of a company that's doing that off the top of my head, but I know of various research groups that are trying that, and I've been pretty surprised by that. That was a cool use of quantum networked technologies. Yeah. It's not really data science related in that context, but it's generating really, really cool data for our astrophysics friends to analyze and maybe find new stuff.
Absolutely. And I guess as a brief diversion, I'm curious what kinds of capabilities quantum networking enables as far as things like space exploration or just sort of spatial communication.
So, turns out there is such a thing as quantum enabled communication. For example, for a dedicated moon or Mars link. Actually, I put out a peer reviewed paper together with my colleague on this exact topic. It's of interest to NASA, and part of it is overcoming some of the detection limits from classical detectors. So you're, encrypting and then using this joint detection scheme that we propose. So there are applications actually of such quantum protocols and, these dedicated space communication links. Another related area is, where people are talking about, using the satellite, creating this fabric, right? So that's good. But if you could do that and share quantum information across it, then it's even better. And I think that that's an application we'll start to see, various satellite-based startups explore in the near term. Yeah.
Definitely lots of interesting things to dig into. And in terms of your own experience of working in this field and starting Aliro and working with some of your design partners, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
Oh gosh, this is a long list, but let me pick maybe the top two. I think the first has been that hardware just takes longer to arrive. And this was before supply chain issues. So we just learned that the hard way, that making stuff takes time and it never happens on time. So, working with some of our component vendors, we realized that we really need to, build in plenty of buffer, especially because of the, level of specialization of these components. And now with trying to navigate not just supply chain issues, but also supply chain security, we really need to allocate a lot of time for that. And initially we thought it's just us. So that was, part of the lesson we learned is that no, it's not just us. In fact, every company out there is facing this. And the sooner we get that information out to our partners and customers, the better off everyone is. So that's something that we and others learned. And now we've started to have share Slack channels and discussions around, getting specialized parts from particular other vendors. Another lesson that, I think has been interesting for us is to really validate the claims that are coming out from folks that don't have peer-reviewed publications to back it. I think that was, another one that I personally learned. I think coming from an academic background, I always thought, well, if somebody's reporting on it, surely there must be some amazing paper or IP behind it. And in many cases, that was true. But there were some cases where that wasn't true. And I was unpleasantly surprised because, I would look at it and say, oh gosh, they've done everything that we wanted to do. I had to wonder how they've done it. How did they figure this out so quickly? And that led to, me then realizing, oh, wait, the way they're saying they've done it, it's actually not making sense. So yeah, those have been a couple of, lessons for me coming from an academic background to this very fast moving tech field and lessons that I've learned personally.
For people who are interested or curious about the capabilities that these quantum technologies and quantum networking protocols enable, what are the cases where it's the wrong choice and they should just stick with classical networking and not wait around for the promised future of quantum networking capabilities?
I think the consumer case is something that I pointed out, right? If you're looking for your favorite service provider to offer entanglement as a service in the next 18 months, or if your service provider is doing that already, you really ought to think about, am I using it for a quantum application or is this a cool fact? As these devices and networks become more generally embraced, I think you'll see a transition and that'll be, the right time to start to embrace these as a personal consumer.
As you continue to work in the space and push forward the technologies and the capabilities for quantum technologies and quantum networking at Aliro, what are some of the things you have planned for the near to medium term or particular areas of research that you're excited to dig into further?
We're really excited about repeaters. We're really excited about various repeater technologies. So, whether it's going to be solid state, whether it's going to be these atomic memories, then going to a repeater, whether there's going to be a totally different repeater architecture or photonic that reveals itself. That's something we've been very excited about because that is the key limiting factor in the speed of these networks at the moment.
For anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
I think there are a lot of gaps. I'm going to give the quantum answer. That's what I experience. I think there's a gap in the various quantum tools that exist to write programs, test things out without access to all different types of hardware that exist, right? So, you can get access to superconducting computers relatively easily via IBM or these other big providers. But some of the other types of qubits, trapped ion or all photonic, the access has been limited for individual users. And sometimes you just have a question like, hey, I just want to test this out. And I don't actually want to run a high value calculation, nor do I want to set up a calculation a collaboration to do one calculation. So it'd be really helpful to have tools that, allow you to do that, whether they're really, fancy simulators running in the background or a set of calculations somebody's run and just made available to addressing these questions. But yeah, if tools like that exist, we'd be very, very happy. I would be happy because I have these weird things I want to run sometimes and I just can't do it without this high barrier.
All right. Well, thank you very much for taking the time today to join me and share the work that you're doing at Aliro and some of the research that you've done in the space to enable these quantum networking technologies. It's definitely a very fascinating field and one that I'm excited to see come to fruition. So I appreciate all of the time and energy that you and your team are putting into that. And I hope you enjoy the rest of your day.
Thank you.
Listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.
La 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 la